Hey, this is Professor Bennett from digitalaudiotheory.com. Now, in the last programming example, we took a look at how to create a complex phasor and rotate it in MATLAB and Octave. In this example, we're going to look at combining two phasors together to create beat frequencies. Now, musicians will already be familiar with the phenomenon of beat frequencies. Beating occurs when two sounds of nearly identical frequencies are played simultaneously. For example, when tuning an instrument. When two tones are nearly the same, a modulation of amplitude can be heard. And the closer together these two frequencies come, the slower the modulation will be. Think about tuning a guitar, and as you turn that tuning peg, the rate of that beating will vary. Now, Richard Feynman, the famous physicist and educator, taught us regarding light waves that signals of two slightly different frequencies can be represented differently. They can be represented as, one, a signal that's the average frequency of the two, and secondly, a signal that is the difference of those two frequencies. The first one acts as the carrier, the second one acts as the modulator or the beating frequency. Let's take a look at this. Let's begin with a cosine of 100 hertz here. 2 times pi times f times t. Now we're going to have a sample rate here of 1 over this number, 10 kilohertz. So we're going to start at time 0, and every 1/10,000th of a second, or every 0.1 milliseconds, we're going to go all the way up to 1 second. So this is our sample rate, our time vector, and our very first signal, x1. Okay. Let's listen to x1 with a few different frequencies. So this is at 100 hertz. Let's listen with it combined together at 101 hertz, 102 hertz, and 103 hertz. So a 1 hertz delta, 2 hertz delta, and a 3 hertz delta. Now these are actually going to be clipping my DAC because I'm not scaling these down, and these are going to go out of range. But it's okay, we're just listening for the beating. Pretty neat. So for this programming example, we'll show that a sum of two cosines with nearly identical frequencies is equal to a carrier with the average of their frequency multiplied by a modulator of half of the difference frequency. So we have already set up our first signal at 100 hertz, x1. We're going to also create a second one, x2, with a frequency of 104 hertz. Let's listen to them together. There we go. And if we plot them, interestingly, we see some carrier frequency with some amplitude modulation. Interesting. Now, let's test out Feynman's theory here. Let's take the average frequency of these. So the average of 100 and 104 is going to be 102. That's right here. So we're going to take 102, make a cosine out of it. So that's going to be the carrier frequency. And we said that the beat frequency is going to be equal to the difference of a cosine with the frequency that's the difference of those two over 2. So the difference of a 104 and 100 is 4 hertz. If we take half of that, that's 2 hertz. So there we are right there. Let's create our modulator. And if we combine, if we multiply the carrier and that beat frequency together, we're going to produce x3. Now, if this x3 truly is the same as the sum of x1 and x2, then if we hold on and plot it, then it should exactly overlay what we see here. There we go. Look at that. So I can come in here and maybe even, let's open this up. If we take this, we can delete x3, and we can see that x1 plus x2 is exactly underneath. Interestingly, we can plot the beat frequency by itself here. So let's do that. Pull it up. Here we go. Here's the beat frequency. Now you'll notice that the beat frequency only has 2 cycles here. 1, 2, right? But what we hear is 4 cycles. And that's because the ear can't distinguish between the positive phase of this beat frequency and the negative phase. So we hear this as 4 Hertz as the true delta. All right, that does it for Chapter 2. The next programming example is going to be from Chapter 3, covering the topic of sampling. Hope you enjoyed. Till next time.